the doing is going to come from experiment 12, so the reaction you're going to use this week is in experiment 12. There's a little bit of information in experiment 13 you'll need as well, but most of your pre-lab is going to come from experiment 12. You'll have your 10th quiz next week, your last week. Next week, we'll be doing the last experiment since we only have a week left after Thanksgiving. So next week will be the last experiment, experiment 14. Your experiment 8 and 11 report is due, so remember pre-lab and experimental for 8 and 11 are separate, but you're going to write a conclusion for both of the experiments together. Make sure to get your GC data for both 8 and 11 from your lab prof. I have run all of the samples I was given, so they have all that data. So make sure you get that this week from your lab prof. For registration, the Chem 256 labs are all really full right now. If you did not register for Chem 256 lab or did not get on a wait list for 256 lab, see me ASAP right after lab lecture today, because I need to know who those names are, okay? And then since we're getting to this time, start reminding you about our final exam. Our exam is Friday, December 12th from 12:30 to 3:30 in this room. So it's the last exam time of finals week. Everybody will get together in this room and take the exam all at once. There won't be any early exams or anything like that. It'll all be given that Friday from 12:30 to 2:30. So bad news is it's that Friday. Good news is it's Friday, December 12th, not like Friday, December 23rd or something like that. So you should still have ample time to get home for Christmas. A couple reminders for your experiment 8 and 11 GC dates. So you need to look at both the peak tables and peak lists that you were given, and you should get a list of standard retention times from your lab prof for your GC date, okay? Any peaks you can't identify, peaks that are unknown, you're going to label them as unknown. However, be careful with that. Make sure that they are actually unknown. So remember, if you have trans products, you'll have cis products somewhere, okay? You're not going to have all trans products. If you have cis, trans, cis, and you're missing a trans, the trans is probably in there somewhere, so don't forget to label it. Don't forget about the ketone that comes off a little before your alcohol. Most of the alcohols did form a little bit of ketone as well. So like the heptanones are in the range of about 6.5 to 7 minutes or so. And the heptanols are about 7 minutes. The octanones are about 8.5 to 9 minutes. And the octanols, which you have all on the standard retention times, are about 9+ minutes, okay? So don't forget, you can label those ketones. They're going to be a peak that comes off right before your alcohol, so make sure that you label that appropriately. So really be careful labeling things unknown. Make absolutely certain that you think and know for sure that you can't label it, okay? And use that list of standard retention times. Okay, so let's talk about Diels-Alder reaction, which I know you guys, you haven't gotten to in lecture yet, have you? Okay. It's coming very, very quickly here, okay? So I'm going to preview that reaction, and then you'll see it again in lecture as well, okay? It's named the Diels-Alder reaction because it was named after a guy named Diels and a guy named Alder who found the reaction, as is the case with a lot of organic reactions. It involves what's called a diene and a dienophile. And we'll talk about each of these, how these are important. There is a lot of adjectives that you can use to describe this reaction, okay? It's a concerted mechanism. It takes place all in one step without an intermediate. It has a cyclic transition state, so it doesn't have an intermediate, it's a transition state. You can call it a pericyclic mechanism as well. That involves a redistribution of electrons is basically what's happening with it. It's also called a 4+2 cycle addition. So this is a really key reaction to organic chemistry that's used still quite often. And so what it involves is our diene. So as the name describes, it's something that has two alkenes in it, okay? And the diene needs to be encompassed within the 4 carbons, okay? So we can't have like, 1,6-octadiene or something like that. It's got to be within these 4 carbons. And then we have a dienophile. And that dienophile wants to join with this diene that has a lot of electrons to donate, okay? And so it's this cyclic transition state where we have flow of electrons from the dienophile to carbon 1, then these electrons over here, then these electrons from this part of the diene to carbon 5, okay? And so in the end, you're starting with 3 double bonds. In the end, you end up with a ring, and then 1 double bond, okay? And it gets a little bit tricky when one of these especially is a ring, because then you're making multiple, your product will have multiple rings in it. What is going on during this reaction is you've got this matchup of p orbitals from the dienophile and from the dienophile and from the diene, okay? And so they come together so that you can have this movement of electrons and then that ring formation. So this, in lecture you'll talk about how all of these p orbitals line up with each other to go ahead and react to form this, the ring. So here's an example of a Diels-Alder reaction. So we've got our 1,4-butadiene, and then we've got a malonate here, diester here with a double bond. And so then you're going to come together between this dienophile and this diene, so that electrons are going to move from here to here to here, and we form this ring, and then the double bond. Now the other thing that's really important with the Diels-Alder reaction is you conserve your stereochemistry, okay? So you only get 1 stereoisomer, and you conserve stereochemistry. So that's another really useful thing to have in a reaction where you don't have to worry about a bunch, products of a bunch of different stereochemistry that you have to then sort out and figure out how to purify from each other, okay? So here is a picture of how we get just the one product. What we form with a Diels-Alder reaction is called an endoproduct. And what you get is you want your diene and your dienophile, since it's this interaction of their p orbitals, you want maximum interaction possible. So you want them sitting right on top of each other to get that interaction, okay? And so if they bond like that, you'll get this endoproduct. If they are opposite from each other, you'll get the exoproduct. And so the exoproduct isn't formed because you need that maximum overlap of the p orbitals to get the reaction to take place, okay? And so this would be the endoproduct. This guy here would be the exoproduct. So keep in mind, you're always forming the endoproduct when you're doing a Diels-Alder reaction, okay? So couple things that are important to this reaction are both the diene, like I said, and the dienophile. it forms what is called an S-cis conformation. So it always takes on the S-cis conformation. So when you're looking at it, like when we were looking at at the butadiene, this is S-cis, okay? So you want these, your carbon 1 and your carbon 4, as close to each other as possible so that they can react appropriately. If you have like this for your diene, then you don't have both ends of it close together to get your ring formation, okay? So you'll always get this S-cis conformation. You're always forming this cyclic transition state, so you need this to happen. It can't like bond here and then come back and bond here. You need everything set up for that transition state. The dienophile means that it's diene loving. It wants those electrons from the diene, okay? And so the more electronegative the groups on the dienophile, the better, okay? So for example, if we just had ethylene, this could be a dienophile. However, it's not very electron withdrawing, okay? So, sorry, instead of electronegative, electron withdrawing. We're going the opposite here. So you want a more electron withdrawing groups. So you want it to be depleted of electrons, okay, or electron density. So you want it to need that electron density. So ethylene itself, you could react it in a Diels-Alder reaction, but it wouldn't react very well. It wouldn't react very quickly. But if you start putting electron withdrawing groups on either side of the double bond, then that makes it a much better dienophile, okay? So you could use something like this guy here. Propanal. So we've got still basically our ethylene piece, but now we put the aldehyde on it, making it more electron withdrawing. Now it'll be more likely to react with the diene because it needs some electron density. Same with something like this guy here, putting an ester on there. So ethyl propanoate. Because we've got this ester group on here, it makes it more electron withdrawing. So it makes it more readily wanting to react with any diene in the Diels-Alder reaction. And so with this, like our dienophile, I'll show you here in a little bit, we actually have a couple of electron withdrawing groups. Yeah?
And when you say electron withdrawing, is that like the opposite of electron negative?
Well, you don't want this to be, what I was trying to say is you don't want this to be really electronegative.
The entire molecule?
You want the groups, so you want the electron withdrawing groups wanting to pull electron density away from this double bond. So instead of just having a hydrogen here, this is more electron withdrawing, more pulling away from it.
Okay.
Okay? So electron withdrawing is better description than electronegative, because that gets confusing whether you're talking here or here. But you want the groups that are actually attached to the carbons of the double bond to be electron withdrawing versus being electron donating. Okay. So the more pull of electron density you can get, the better off your dienophile is going to be, and the faster it will react. All right. So like I'll show you here in a minute, our dienophile for this week, it actually has 2 electron withdrawing groups on it, so it makes the reaction really quick, all right? It'll be the quickest reaction you've seen yet, okay? So our reaction this week, this is our dienophile here, okay? So we basically, even though it's symmetrical, we basically have 2 electron withdrawing groups here on the N-phenyl malleamine, okay? And our diene is cyclopentadiene. So we've got 1, 2, 3, 4 are the carbons of the diene, and then we've got 5, 6 of the dienophile. So you've got the reaction here of electron movement between the double bond here, down here, back over here, to then form this ring. So this is the ring that is formed right here. These 2 bonds are the new bonds that are formed, okay? And then again, here we've got our endo product, okay? And so when you're talking endo, it gets a little bit confusing what you're talking about, but you're looking at it being syn relative to your largest bridge, and in this reaction, this is our largest bridge, versus it being the other direction, which would be exo. So if we move this guy up, we would have the exo product, which isn't formed, okay? And so, like I said, this reaction is really fast. We have you reflux it for 10 minutes, but you don't really even need the reflux to get it to go. It goes instantaneously, okay? So the reaction itself and doing the reaction this week is going to kind of be the easy part. The rest of it, where we're going to use thin layer chromatography, which I'm going to talk to you here in a bit about, that's going to be the more difficult part. Yep.
So would the reaction run faster if you had a stronger electro withdrawing group on it?
Right. Yeah. Yeah. The more you can pull electron density from here, the more willing it's going to be to react and get that electron density back. Okay. Now, the trick to the reaction that we're doing this week is we need cyclopentadiene, and in order to get cyclopentadiene, you can't just have it laying around. We don't buy a bottle of cyclopentadiene. What we have to buy is dicyclopentadiene. So it sits around in a bottle as its dimer, okay? And because the cyclopentadiene has a really good setup to have a diene and a dienophile, and so it can do Diels-Alder reactions with itself. And so what we have to do is what's called cracking the dicyclopentadiene, and so it's a retro Diels-Alder reaction. We're basically going to undo the Diels-Alder reaction that gets to the dicyclopentadiene to get singularly cyclopentadiene, okay? So what will happen this week is right before you do the reaction, we will crack the cyclopentadiene for you, and then we will dispense the cyclopentadiene for you, okay? So you won't do this part. This will be taken care of for you, and then we'll dispense it, all right? So as far as the actual reaction, like I said, you're going to have your N-phenylmalonyl-amide. You dissolve it in ethyl acetate. The ethyl acetate's in the reagent hood. It needs to be as dry as possible for this reaction. So also keep your glassware dry. Don't have any like visible water in it. We don't have to dry it like we did with the Grignard reaction, but you don't want it visibly wet, okay? So use the ethyl acetate that's in the reagent hood. Now the thing to be careful of, in a minute we're going to talk about your eluent for TLC. The eluent is 1:1 hexane ethyl acetate, and the solvent you need for your reaction is just ethyl acetate. So make sure you grab the right bottle when you're setting up your reaction, okay? So you're going to dissolve your dienophile in the ethyl acetate, okay? Once it's dissolved in the ethyl acetate, then you'll see your lab prof, they'll give you the cyclopentadiene, all right? Then you're going to want to do, and in a minute this will make more sense, you're going to spot this for TLC, then you're going to reflux it for 10 minutes, okay? Then you're going to spot it for TLC again, and then you'll go through the workup, and then you'll be analyzing your final product as well, okay? So in a minute, I'll explain what all that means, But just keep in mind that those are steps that you need to take along the way. Besides just running the reaction, you need to worry about making sure you're spotting it for the TLC analysis, okay? The other nice thing about this reaction is it's done in 10 minutes after 10 minutes of reflux. You distill off the ethyl acetate, so just keep it hot after the reflux. You don't want to cool it down at all because you're going to convert it right to distillation. This whole time you're doing it in a water bath, so you want to keep that water bath hot. Once you do the distillation, then you're going to precipitate the solid with hexane, filter it, recrystallize with ethanol and water, and you should get this really nice white, solid, crystalline solid. Looks really great, okay? So it's like the best looking product that we'll make this semester that you'll actually keep that product, maybe except for compared to experiment 1, okay? So it looks really nice. It's really easy reaction, okay? So, but just make sure you follow the steps and spot for TLC when you need to, all right? Okay, so now we'll look at thin layer chromatography. So this is what I'm talking about, is we're going to be looking at something like this that involves plates like that. And that's what's covered in experiment 13. So here we go with another chromatography, our third one of the semester. As always, we have our stationary phase. And we'll have our mobile phase. So with thin layer chromatography, our stationary phase for the most part will be silica. Usually when you use it, you're using silica. And this is going to be on, this week, it's going to be on TLC plates themselves, okay? I'll show you what those are here in a minute. So it's silica that's on a flat plate with a plastic backing, okay? Your mobile phase is your eluent or the solvent that you're using for TLC. So I just a minute ago talked to you about what your solvent is. It's 1:1 hexane ethyl acetate. That is your eluent or your solvent for TLC, and that's going to be your mobile phase, all right? Now, gel permeation chromatography, we had separation based on size. Gas chromatography, we had separation for the most part based on boiling point. This separation is based on the polarity of the compounds being separated. And there's this interaction going on with those compounds and the stationary phase and the mobile phase. But it's all based on polarity. Okay? And so what you've got going on is this equilibrium. And you've got on one side the stationary phase, and the other side you've got the mobile phase. And so the compounds that you are analyzing are going back and forth between these two, between the stationary phase and the mobile phase, okay? And depending on the polarity of the compound, it will spend either more time with the stationary phase or more time with the mobile phase, okay? If it spends more time with the stationary phase, it doesn't move as much as with the mobile phase, okay? If it spends more time with the mobile phase, it'll move more because it's not hanging out on the stationary phase. So you've got this equilibrium going back and forth, all right? And when we talk about the stationary phase, we talk about the compound that we're looking at is adsorbed, so not absorbed, but adsorbed on the stationary phase. So it goes back and forth between being adsorbed in the stationary phase or moving with the mobile phase. Now, the stationary phase that we're using, the silica, is very polar, okay? And no eluent that we will use will be more polar than the silica. So the stationary phase is going to be our polar component, okay? And then we can adjust our mobile phase to be more or less polar as we need to, okay? But this is really key. Your silica, you're not going to have any eluent that will be more polar than the silica. It's really hard to do. In order to be more polar than the silica, you almost practically have to dissolve it to be able to do that, okay? And we don't want that because then our separations won't work. So what you're going to have is the TLC plate is going to be something like this, okay? So you're going to get plates that have already been cut for you. You don't have to cut them. They've already had what we call the origin line drawn on it, so you know where to spot your samples on, okay? And then you're going to put it in a developing solvent. So I told you that's the 1:1 hexane ethyl acetate. In this developing chamber, you're going to fill with just a little bit of solvent. You don't want it to go above that line when it's developing. So when you set it in the chamber, make sure you have a small enough amount. You don't go above the origin line. You also have filter paper in here that absorbs that solvent. And so then you've got this chamber where you have the liquid solvent down here, but it's also filled with the vapors of the solvent to keep everything at equilibrium. So you don't have a difference in how it travels up the TLC plate because there's a difference in what's in the liquid and what's in the vapor itself, okay? So you've got this equilibrium between the solvent vapor and the actual liquid in the developing chamber. So this is more what the TLC plate will look like, okay? So you set it vertically and you're going to spot right here on this line, okay, on that origin line. Now, we'll talk here in a minute what RF value means. But in general, because the stationary phase is very polar, more polar compounds are going to want to hang out with that silica. So they will travel less far up the silica, okay? Because they want to hang with the silica. They don't want to go into the eluent as much. So they aren't going to travel with the eluent. Less polar compounds will travel farther up the plate because they want to hang out more with the eluent and less with the silica. Okay? And so that's how we get a separation between the compounds that we're looking at is based on that polarity of what's going to stay with the silica and what's going to hang with the eluent more. But keep in mind, there still is the equilibrium going back and forth. Every compound is going to go back and forth between the silica and the eluent. Okay? So we can manipulate this situation to help get better separation if we need to. So a more polar solvent not compound, but solvent or your eluent, will cause the compounds to travel farther. A less polar solvent will cause the compounds to travel less far. Okay, so when you're talking about polarity, you have to keep in mind, are you talking about the polarity of the compounds, or are you talking about the polarity of the eluent? Because you've got the opposite effect going on, okay? So polar compounds don't travel very far. Less polar compounds will travel farther. If you manipulate the solvent, though, more polar solvent will cause all the compounds to travel farther, because even those polar compounds are going to want to hang with that polar solvent. And less polar solvent will cause the compounds to travel less far, okay? So that's what we're looking at here in this example. We've got this TLC plate that we spotted on the bottom. Then we developed it in the developing chamber. So you're going to let solvent travel up that TLC plate till about 1 centimeter from the top of the plate. Then you pull it out, mark that origin line in pencil, and then you're going to look under UV light to see what you've got, okay? So the TLC plates that we have a dye that's UV active, and so if you have spots on the TLC plate, the way you'll see them is by looking, as long as the compounds themselves are UV active, you'll look under a UV light to be able to see what spots are on your TLC plate, okay? And we've set it up so that what you're going to be looking at is all UV active so that you can see it, okay? So compound A didn't travel as far, so this is more polar than B or C. And compound C traveled the farthest, so it's less polar than B or A. Does everybody see that? Based on what we just talked about? Okay. So if we changed the solvent, changed the eluent, we could get all of these compounds to move farther, okay? And the thing is, you can't get them to move beyond the solvent front. Okay, that's always going to be the stopping point. They're not going to go beyond the solvent front unless you forget to pull your TLC plate out of the developing chamber, and then it'll basically run off the TLC plate, okay? But if you marked your TLC plate appropriately, you're not going to go leap beyond the eluent. You'll always be on this side of the eluent, all right? So what we use to describe this relative polarity of compounds is the RF value. And that's defined as the distance from the origin traveled by the compound. So our origin, again, is this line here. This distance divided by the distance traveled from origin, or the distance from origin traveled by the solvent. So this distance here, okay? So first of all, you've got a distance divided by distance. Do you have any units on an RF value? No units, right? And what can you say about that number? You've got this number divided by this number. It's always going to be a decimal less than 1, right? So your RF value will always be a decimal less than 1. If a compound has a bigger RF value, what can you say about it? It's what? It's based on what we just talked about. It's less polar. So compounds with greater RF values are less polar. Compounds with smaller RF values are more polar. Does that make sense? Because it's all related to how far it travels, okay? The other thing that's nice about RF values, for a given system, you can use those to characterize what you are looking at, characterize the compounds that you're looking at by TLC. And so what I mean by a given system is using the same solvent system, you can compare relative RF values, okay? Because they should stay the same. So even though your solvent may travel farther or not, this ratio of how far the compound travels versus how far the solvent traveled will stay the same, all right? So this week, when you're using the 1-to-1 hexane ethyl acetate, even though you may be looking at things on different TLC plates, their RF values can be compared to each other, okay, because you're using the same solvent system, all right? And so what we're going to do this week is we're actually going to use standards to help you figure out what is your product and what is your starting material. So we're going to have TLC standards that you spot on your TLC plate along with your reaction mixture or your final product that are the starting material, the N-phenolmethylamide, and the final experiment 12 product, okay, after you've gone through the Diels-Alder reaction. So you'll have a standard of each of those. So you can use that for comparison to figure out which is what spot on your TLC plates, okay? So for this week, before I go looking at things that happen as we change things, for your experiment 12 product, you're going to need at least 3 different times that you spot a TLC plate. Okay? So you're going to spot the TLC plate at the start of the reaction. So you're going to have your N-phenolmethylamide dissolved in your ethyl acetate. You're going to go get your your cyclopentadiene from your instructor. The moment you get back to your hood, you're spotting that reaction because the reaction's so quick. If you wait around, you're not going to basically get the start of your reaction. It will have all reacted on you. Okay. So before you get the cyclopentadiene in your round bottom flask, you're going to need to make sure you have a TLC plate ready to spot, and you're going to need to make sure you have what are called spotters. So we're going to teach you this week how to pull glass capillaries to make them really thin, so when you spot them in a liquid and then put it on a TLC plate, it makes a really small spot on the TLC plate, okay? So you want your TLC plate and your spotters ready to go. As soon as you get the cyclopentadiene in, you're going to spot that TLC plate, okay? Then look under the UV light at what you've spotted to make sure it looks okay. Okay, so you can look at the spots before you develop them to make sure you've got enough on there, make sure that it's in the right spot, those kind of things, okay? Because once this reaction gets going, there's really no going back to the starting point, okay? So spot on the TLC plate, look at what's going on, okay? Then you're going to reflex the reaction. So the next spot, you're going to have the end of reaction or the end of the reflux. Okay, the spot again. Then you're going to have your final product after recrystallization. Now, some profs also have you kind of do an intermediate here of your crude product before you crystallize and then your final product, or they may just have you look at your final product. For this final product, it's a solid, okay? So whether you're looking at the crude product or the final product, it's a solid. You can't spot a solid on a TLC plate. You need it dissolved in something. And you can't spot a neat liquid of something. You need it dissolved in the solvent because it's too concentrated, okay? So you're going to dissolve that final product. There's instructions in your lab manual to dissolve it in ethyl acetate. And you're going to use red can ethyl acetate for this, okay? So you're going to dissolve it a little bit in ethyl acetate and then spot that on the TLC plate. Now keep in mind, there's also the standards to spot with on the TLC plates too. So your lab prof will tell you for your TLC plates how they want everything lined up, okay? But count on at least these 3 times you're going to be spotting the reaction, okay? And so what we're going to do is we're using TLC to monitor the reaction. So say this is time 0. We've got one standard, another standard, and then the middle is our reaction. So based on these standards, A is probably reactant standard, C is probably product standard, the middle is the reaction, okay? And this isn't necessarily how experiment 12 is going to look like. This is just an example, okay? So then you let the reaction progress. You still have your two standards. They're not going to change. But all of a sudden, that middle column, that's the reaction, now you've got this top spot is also being converted to this bottom spot is growing in, okay? And so you're seeing progress of the reaction. You've got starting material going to product, okay? Then as you go, what you want to see at the end is no starting material and only product in that middle lane, okay? And so that's how you monitor a reaction with TLC. Does everyone understand that? And so that's why we're going to sample at each of those three spots so we can monitor the reaction, all right? But if you don't do things at just the right time, especially the start of the reaction, you're going to quickly get to this one before you ever see this one, or even see a middle one, okay? So that's one way that TLC can be used, is to monitor a reaction. Another thing that TLC can be used, and you use this next semester, is actually for column chromatography and monitoring what's going on with column chromatography, okay? So we'll use it multiple ways next semester for monitoring reaction as well as monitoring what we call running a column. So what you learned this week, don't forget it. You need it for a good portion of next semester, okay? Including learning how to pull spotters, which is maybe the most difficult part of this whole thing, is the dexterity and the, like, just the right pulling and heating of these fine capillaries to make the right spotters, okay? So I want to go through here now a couple examples of how you could change what is going on with TLC. And then we'll look at some specific things for your product this week. So say we've got a reaction here, or a TLC plate, and we've spotted on the TLC plate, and we developed the TLC plate, and so we have a spot like this, okay? And when you are measuring for the RF value, always measure into the center of the spot. So this over this would be our distance traveled from the origin to the spot, and then here to here would be our distance traveled from the origin to the end of the solvent, okay, for calculating. So we use this number and this number for calculating RF value, okay? So we've got this spot on the TLC plate that's kind of running close to the baseline. You don't want spots really hugging the very bottom of the baseline to be able to figure out what's going on, because sometimes other things can be hiding in there, okay? So if we wanted to make this spot have a greater polarity, what would we do to the solvent? We would use a more polar solvent, okay? So like this week, we're using hexane ethyl acetate. A lot of times with TLC and column chromatography, you use a mixture of something relatively nonpolar. In our case, it's the hexane, and something more polar, which is, in this case, is the ethyl acetate. So what would you do to that ratio to make it more polar? More ethyl acetate relative to hexane, right? Okay. So then hopefully we get something maybe like this. Oops. But then we've moved, that spot has a much bigger RF value, okay? Now what do you want to do if you want to lower the RF value? Then you, more hexane, right? You want to make the solvent less polar. So if you want to drop the RF value, less polar solvent, so in our case, more hexane or more of the relatively nonpolar solvent, okay? So now, looking at something like this, we've got a couple spots. What is the more polar spot? A. What is the less polar spot? B. Okay. So keep those all of those things in mind, okay, as you're thinking about thin layer chromatography and thinking about this week's experiment and explaining this week's experiment, and also for the quiz and so forth. How the polarity of the compound is related to what RF value it will have versus the polarity of the solvent, how that changes things, okay? Because you've got two different things going on. Now, one thing that does not happen with TLC is it's not like a melting point, okay? So you're not going to get, like if you get a smaller RF value than you should have had, you can't say that it was depressed because there was impurity, okay? So it doesn't work like a melting point or a boiling point. You can't depress an RF value, all right? It should be consistently the same RF value. What you will see, if there was an impurity, then you'd see another spot, okay? But you're not going to have this spot change RF value because there's an impurity present, all right? So you'll see more spots, but you won't change your RF value based on impurities. Does everyone understand that? Okay. So for experiment 12 product, first of all, you're going to have this TLC analysis, follow your instructor's directions for what you're going to do. Then you need to collect the IR spectrum of your product. It's a solid, so you're going to collect it just like you did with polystyrene. Okay? There is no literature IR spectrum, but on Moodle, there'll be both starting materials and a standard IR for the product. So I'll post those this week, okay? The other thing you need to collect is, well, and even before all this, of course, yield. We always collect our yield. Then we're going to need a melting point, and you may need to wait a little bit to get this because you're recrystallizing from ethanol and water, so it may take a little bit for that solid to get dry. Same with the IR spectrum. If you see an OH stretch in your IR, it may be because of the ethanol and water. It may not be completely dry, okay? So you need a melting point. There's no standard for the melting point, so you're just going to collect the melting point of the product, right? So you need these three things besides the TLC analysis: yield, IR, and melting point. Experiment 12 is like experiment 4 in 6, so there's a report form to fill out, okay? So you're going to give all your information, the structure of the experiment 12 product. You're going to reproduce your TLC plates on this form, okay? And so you want to, for the description of the spot, tell me what that spot is. Is it the starting material standard? Is it product standard? And then give me the RF values for all the spots in that lane, okay? So you do that for each lane, A, B, and C. And depending on how many plates you have, you may only have 2 plates, or you may end up having 3 TLC plates. Okay, but fill it out for each lane and each spot. Does everybody understand that? Okay, backside. IR. So you'll put in all the information for the IR, and you can compare your literature, can be compared to the IR spectra that will be on Moodle. But make sure you fill this out completely and analyze it. You may or may not have an IR spectrum that completely makes sense, okay? So if there's peaks in there that don't belong, make sure you identify those peaks. Then you will write a conclusion and attach the conclusion to this along with the IR data, okay? And your instructor will give you more specifics for that conclusion. So experiment 12 is a worksheet, not so much a report in your notebook. Okay, so one more thing that'll be very helpful for your pre-lab is information for the cyclopentadiene and phenolmethylamine. Here is your final product, and here, so you've got to collect the melting point. There isn't a standard to use for a mixed melting point, but here is what the melting point should be, so you have an idea of what that melting point should be. All right? So you can use all of this data for your pre-labs, okay? And make sure your pre-lab is complete. I know in grading some of my experiment 7s, pre-labs weren't so complete. So make sure your experiment 12 pre-lab is complete. You get all the other things that go in the table. So this isn't everything that goes in your data table. This is just helping you out a little bit with some information. So you may make sure and get all the other pieces in there, solvents and so forth, in your physical data table, okay? And then once you have that, if you don't have any questions, then you may go.